Exploratory data analysis. The way we explore the data depends on the types of variables. So what do we mean by the word types of variables? Variables we can categorize into either quantitative numbers or qualitative categories. Those that we measure, we count, those are quantitative data. Those that we classify based on their characteristics are what we call qualitative data. Examples of quantitative data, it could be either discrete or continuous. For discrete data, it is examples numbers of children. For continuous data, things that we measure, for example, the height, the weight of the patient. For qualitative data, although it takes coded numerical values, they are not continuous data. They are really still qualitative data. For example, ordinal data, like we have for the pain severity. So when we code the pain severity from 1 to 5, 1 the least, 5 the most, then it became an ordinal data set for pain severity. Nominal data is when there is no ranking order. For example, the race in Malaysia, Malay, Chinese, Indian and others. There is no ranking order. So those are what we call nominal data. So that is what we call a nominal data set. So why do we explore? It is the first step in the analytical process. We want to understand, we want to look at the characteristics of the data. We want to look for errors, and if the errors are present in the data set, we want to correct them. Then we look at the distribution patterns of the data, whether it is normally distributed or not. If the data is not normal, you may have to transform the data set so that it becomes normally distributed, so that you can do analysis using parametric methods. Or if you do not want to transform the data, you want it to stay as it is, maybe you will need to analyze the data set using nonparametric technique if the data is not normally distributed. So we mentioned about data screening. We want to screen for errors. One of the most common command that we use to screen for errors is the command frequencies. So when we run frequencies, we may detect inappropriate responses. For example, this data from Kelantan, when we are doing a study on small for gestational age. So we asked the mothers how many children they already have. So some of the mothers stated that they have 15 children. And not only that, she is currently pregnant with the 16th child. So if we ask around, I don't think anybody among us are currently pregnant with the 16th child. So if we do checking, we can see whether the data makes sense or not. Surprisingly, the data for the 15, for the parity of 15, it shows that it is true, it's correct. Okay, patient is already 44 years old, but she has been giving birth since the day she got married. Okay, every year one, so that's why she got 15 children already. Of course, there are issues here. You can see here, housewife only 25 years old, already have 10 children, and yet there's only 7 staying with her at home. Okay, so data set like this, we have to check: are these 10 children all of them her child, or only maybe 5 her own child, maybe the other 5 belong to another mother? Why we do frequencies? Because sometimes we may identify that we have made a mistake. For example, here we have a mother whose height was stated as 3.7 meters, which is wrong. So the data set you can see here 1.3, 1.4, 1.5, 1.6, 1.7. So suddenly you have a mother who is 3.7 meters tall, which does not make sense at all. Sometimes when we code the data, we do not use numbers, instead we use letters. So we have F for female, M for male. With letters, there may be some problem because we have capital letter and we have small letter. So if it is capital letter and small letter used together, when you run the analysis, suddenly we end up with two kinds of male gender. Okay, the male which is having a small letter and the male which is having a large letter. That is why the data is categorical data. We still code them as using numbers, because numbers, they have no capital letter, no small letter. So for data screening, we can also look at the measures of central tendency. As you can see here clearly, there is a problem here. Why? First and foremost, minimum weight of 32 is acceptable. There are some pregnant mothers who are only 32 kilogram in Kelantan. However, there is a mother whose weight is 484 kilogram, which does not make sense at all. So you better check. So most probably the mother is only 48 kilogram. And how does this wrong entry affects you? Suddenly you're going to end up with a very large standard deviation. Here you have a standard deviation of 33.37, which is very, very big. This is the box and whiskers plot. If you are looking at the box and whiskers plot, please take note that black mark in the middle is not the mean. The black mark in the middle is the median. The top one is the 75th centile. The bottom one is the 25th centile. Okay. So when you run your data screening, you can make use of graphical tools such as the box plot. Here you can see clearly we have a problem. All the data set are beautiful, all below 100 kilogram, but we have one here 484 kilogram. The data set is record number 73. So this record number 73, we have to go back and check, is it really the patient 484 kilogram, or is she really only 48 kilogram? So we have shown you about wrong or extreme values. So what should we do? You should always check with the original data source, which is the questionnaire. If your data was incorrectly entered, please do the necessary correction in your data set. This correction must be done before you proceed with anything on your analysis. Okay, that is the story about data screening. Now we are going to look for data distribution. So to understand data distribution, you have to understand that in the past, to decide on the data whether they are normally distributed or not, you must look at this following item. We look at the mean, we look at the standard deviation, we look at the skewness, we look at the kurtosis. Based on these four key figures, we can decide whether the data is distributed normally or not. Okay. So what do we mean by normal distribution? So normal distribution is represented by a family of curves defined uniquely by two parameters, which is the mean and standard deviation. If you have the mean and standard deviation, you can get the distribution. So you can see here in the middle there, that is the mean value. Okay. Next line is the 1 standard deviation, 2 standard deviation, and 3 standard deviation. So the bell curve here is drawn based on the mean and standard deviation of this sample. The curves are always symmetrically bell-shaped. How far it is compressed or flattened depends on the standard deviation of the population. Okay, so please take note of that. So if the observations follows normal distribution, a range covered by 1 standard deviation includes about 68.3% of the observations. A range of 2 standard deviation above and 2 standard deviation below will cover about 95.4% of the observation. A range of 3 standard deviations and above and below will cover 99.7% of the observations. Okay, so those are the explanation of the normal distribution. So why are we so fixated with normality? Why do we have to check whether your data is normally distributed or not? Because this dictates the type of analysis that you can run on your data set. If your continuous data are normally distributed, then you can use parametric method of analysis. Examples of parametric method of analysis students t-test, ANOVA, PET t-test, Pearson correlation, and linear regression. If a data is not normally distributed, then you have to use non-parametric method of analysis. So non-parametric method of analysis, for every one of parametric method of analysis, there is an equivalent non-parametric method of analysis. For example, for the t-test, students t-test, we have the Wilcoxon rank sum test. For the ANOVA, we have the Kruskal-Wallis one-way ANOVA test. For the PET t-test, we have the Wilcoxon sign rank test. For Pearson correlation, we have the Kendall correlation and the Spearman rank correlation. So how do we decide whether your data is normal or not? There are a few ways of checking for it. You can either do the graphical method or do the statistical method. For graphical method, we will cover one by one: histogram, stem and leaf, box plot, normal probability plot, and the detrended normal plot. If the data you want to check statistically, the name of the statistical test for normality is called Kolmogorov-Smirnov statistics. The other figures that we look at is the mean, median, and mode. If the mean, median, and mode are the same, they are normally distributed. We look at the skewness and kurtosis. So you can see here, skewness is 0. If skewness is 0, means that it is symmetrical. Kurtosis is 0, kurtosis is symmetrical. Okay. If the kurtosis, the value is positive, it is leptokurtic. If the kurtosis, the value is negative, it is platykurtic. So who is this Kolmogorov-Smirnov? Kolmogorov-Smirnov is in fact two persons. One of them is Andrei Nikolaevich Kolmogorov and N.V. Smirnov. They came out with the approach for comparison of distributions that does not make use of the parameters. Okay? So it did not make use of the parameters. And this test is known as a Kolmogorov-Smirnov test. When we talk about skewness, we are talking about the extreme values. Here, although the big portion is here, we don't care about here. We care about here. So this is a large extreme values. So why large? X axis, small value, large value. So the skew to the right is due to the large extreme values. For this one, it is skewed to the left because we have small extreme values. Okay, the small extreme values causes this kind of skewness of the data set. If you're looking in terms of the height of the bell curve, we have mesokurtic, leptokurtic, and platykurtic. The one that is tall and narrow is the leptokurtic shape. This one in the middle is the mesokurtic average shape. And then we have at the bottom there platykurtic, which is flat and wide. How do we decide whether the data is normal or not? By looking at the skewness of kurtosis. The acceptable range for normality is between -1 and +1. So you can see here for the kurtosis, the yellow-orange color one, it is nice, mesokurtic in shape, when the kurtosis is near to 0. So that's what we want. Okay. For the data to be regarded as normal, it is ±1. Okay, so let us run the data set. This is the data set of the pregnant ladies. We have 218 of them. We are checking their height. So you can see the height of the pregnant ladies. Okay, started at around 130 something, 138, 39. The tallest is about 167.5. So you can see that in terms of the height of the mothers, the data is normally distributed. The other way of checking whether the data is normal or not, okay, which is what you call the Q and Q plot. This one compares the quantiles of the data distribution with the quantiles of a standardized theoretical distribution from a specified family of distribution. So which family? The normal distribution family. If the distributional shapes differ, then the points will plot along a curve instead of a line. Take note that the interest here is the central portion of the line. Severe deviations mean non-normality. Deviation at the ends of this curve indicates existence of outliers. So you can see here, this is the Q and Q plot. Nice curve. Most of it is on the green line. So we are okay. By the descended normal Q and Q plot, you can see that the residuals are well distributed all over, so there is no clear pattern. So we run the analysis. We look at the descriptives. You can see here clearly the mean is 155.165. The median is 151.90. So we look at the skewness and kurtosis 0.148, kurtosis 0.061. So this is between plus minus 1, so the data is normally distributed. This is further proven by the Kolmogorov-Smirnov, where the p-value is larger than 0.05. If the mean, the mode, and the median are the same, this is what we call as a normally distributed data. Nice bell curve. If you follow the nice bell curve, the mean, the mode, and median should be the same value. Okay, as stated here, we can also check for the Kolmogorov-Smirnov test. If the Kolmogorov-Smirnov test is not significant, like in this case, the p-value is 0.2, then the data is normally distributed. It is very sensitive to the sample size of the data. Okay, so therefore, if you have a very small sample size, the likelihood of getting p less than 0.05 is low. For large sample size, where n is larger than 100, a slight deviation from normality will result in being reported as abnormal distribution. Okay, so after seeing all that, you can conclude that immediately, if the sample size is less than 30, it is always, we always assume that it is not normal. If the data has a moderate sample size 30 to 100, then we rely on the Kolmogorov-Smirnov test. Okay. If the samples are larger than 100, we don't rely on Kolmogorov-Smirnov test, the KS test. Instead, we look at the skewness and kurtosis.